Hello everyone, we are from BMS College of Engineering. Myself Roshini and my teammates Asmitha and Yuktha are going to present on the topic ant colony optimization of the course Nature Inspired Computing. So firstly, what is ant colony optimization? It is a nature inspired optimization algorithm based on the real behavior of ants. It mimics how ants find the shortest path between nest to food and food to nest. It uses pheromone trails as indirect communication. It works extremely well for problems that involve finding best or optimal paths. Why are ants intelligent? As you can see in the picture, ants explore randomly at first. When they find food, they deposit pheromones. Shorter paths receive more pheromone because ants travel back and forth faster. Over time, almost all ants follow the strongest pheromone path. Long paths evaporate and they disappear. So, key concepts behind ant colony optimization are pheromone trails, visibility, probabilistic movement, evaporation, and positive feedback. So, let us see how ant colony optimization works. This is the process flow. First step is to initialize pheromone on all edges. Second step is each ant constructs a solution. Third step, calculate the solution cost. Fourth step, update pheromone, where we add pheromone to good paths and then evaporate old pheromones. We repeat all these steps until convergence. This is probabilistic path selection, where ant chooses next city based on this formula, where it is the product of pheromone and visibility divided by the summation of product of pheromone and visibility. Here tau is the pheromone, eta is the visibility, that is 1 by distance, alpha and beta are the importance of pheromone and visibility. Asmitha will teach about the ant choosing next node.
Now let's look at a simple example of how an ant decides which node to move to next. Here the ant is currently at node 0 and it has three possible choices. Node 1 with desired value A, node 2 with desired value B, node 3 with desired value C. The probability of selecting any node is calculated as the ratio of desired value over the total desire of all available nodes. So the probability of moving from node 0 to node 1 is A by A plus B plus C. This demonstrates how ants probabilistically choose paths rather than deterministically selecting just the shortest one. Next is the random number generator example. To finalize the movement decision, ant colony optimization uses a random number generator. A random value is generated between 0 and 1 and that value determines which node is selected based on the probability ranges. For example, if the random number generated is 0.47 and that falls within the probability range assigned to node 2, then the ant will move to node 2. This technique ensures exploration and avoids the algorithm getting stuck in early paths. Now Yuktha will continue with the next.
I'm Yuktha and I'll be presenting about the ant colony optimization for traveling salesman problem. So the algorithm goes as I'm saying. Step 1, initializing important parameters, that is population size, maximum iterations, pheromone evaporation rate, initial pheromone level, alpha which is pheromone influence, beta which is heuristic influence. Step 2 is objective function and fitness calculation. We'll calculate fitness for each possible tour. Fitness is equal to sum of all distance in a tour. So the goal is to generate feasible solutions. Next, step 3, solution construction. Ant starts moving from random city, move towards unvisited cities, selection based on probability influenced by pheromone and distance. Step 4 is distance calculation. Apply Euclidean distance formula to calculate distance between nodes. Step 5 is probabilistic transition rule. Probability of moving from city I to J is given as the formula below, and tau is the pheromone intensity and eta is the visibility, which is 1 by distance. Step 6, tour construction. Ant travels through all cities until tour completes. Total tour length is recorded. So we'll repeat the same for each ant. Step 6 is pheromone update. Pheromone update is done by the formula tau ij is equals to 1 minus rho into tau ij plus summation tau ij at kth ant on path ij. So step 8 is compare solutions and select best tour. Evaluate all ant tours and we'll choose the shortest path, which is best fitness output. And now Asmitha will continue the next.
Now let us discuss about the strengths and limitations. Strengths, it includes positive feedback, which means good solutions are discovered quickly. It performs very well on complex optimization problems. Ant colony optimization is distributed and parallel, so multiple ants explore simultaneously. It can adapt if the environment changes. With evaporation, it can escape local minima, improving solution quality. Limitations, it may have slow convergence, especially for large data sets. Ant colony optimization is parameter sensitive. It requires high computation for large graphs. Without proper evaporation, the system may stagnate and stop improving. The next is the real world applications: network routing, robotics path planning, vehicle routing and logistics, scheduling and timetabling, DNA sequencing, image segmentation, IoT network optimization. So the summary of ant colony optimization it is inspired by the foraging behavior of ants. It uses pheromone trails and visibility to decide optimal paths. It works extremely well on optimization problems like the traveling salesman problem. Even though the rules are simple, they result in complex and intelligent behavior. Overall, ant colony optimization is a powerful and widely used nature inspired optimization technique. Thank you.